Welcome to this webinar featuring Renesas RZ microprocessor family in optimized HMI designs. We will start by giving a general introduction of how to drive displays, and this will include some commonly used techniques and implementation methods. At Renesas Europe, we are convinced that with RZA, the HMI designer's life in effect becomes much easier. At the same time, the purchasing department will take delight in reduced system costs facilitated by an optimized BOM. My name is Stefan Zank and I will be the presenter of this 30-minute webinar. I am part of Renesas microcontroller and microprocessor solutions team based in Munich, Germany. This will be the agenda of today's presentation. We start by giving information on RZA, the best of two worlds. We will continue with some introduction to HMI technology. We will talk about the standard approach of HMI design, and then we follow on to the RZA optimized approach of HMI design. We will talk about advanced hardware features of RZA for HMI specifically, and then we conclude with an update for tools and software. Renesas RZA is an embedded microprocessor, which in terms of usability and performance is positioned right between highly integrated and easy-to-use microcontrollers and high-performance microprocessors with external memories. The RZA combines the advantages of both classes and is the best of two worlds, so to speak. For many people, the distinction between microcontrollers and microprocessors is just about integrated flash memory, where microcontrollers have embedded flash and MPUs don't. However, microprocessors and microcontrollers actually differ in more aspects. Microcontrollers have very high digital and analog peripheral integration, as well as high-density embedded RAM and flash, which belong to the most important parameters of scalability next to performance. To offer exactly the right price performance point for any application is absolutely required in the microcontroller space, which is the reason for the generally big microcontroller portfolios of several hundred devices per family. That being said, it becomes clear that system cost is one of the most important criteria in the microcontroller space, and also the reason why microcontrollers strive to facilitate single-chip solutions. As far as microprocessors are concerned, performance is usually more important than cost. This means there is a big focus on high-performance cores with high operating frequencies, high DMIPS per megahertz, and multi-core superscalar Harvard architectures. The operating system is also very high on the list. Flash and SRAM are usually external with microprocessors, as these have to be scaled heavily in high-performance applications. The RZA is clearly differentiated in this two-legged market standing right between. The RZA has 10 megabytes of SRAM integrated, which is ample for most HMI applications. Second, the quad-speed SPI flash runs at very high speeds, enabling execution in place, which means code can be executed right from flash. Images to be shown on a display are always stored as raster images in RAM. The memory requirements for this depend on multiple factors, including color depth, which may be 16-bit or 24-bit, and on resolution, which is based on a certain pixel count for a display of a given size. The following calculations depend on the type of implementation. We assume 16-bit color, where 6 bits are used for green because the human eye is actually most sensitive to shades of green. As far as resolution is concerned, in the consumer space, Full HD has more or less become the standard, which is equivalent with 1920 x 1080 pixels. In industrial, we also have a trend to higher resolutions, but here also VGA is widely used, so we work with a VGA example here. So VGA means we have 640 times 480 pixels or 307,200 pixels. The chosen color depths put 16 bits or 2 bytes on each pixel, so we have a resulting 614,400 bytes or 600 kilobytes for the VGA image. Anybody who has worked with graphical design tools knows there are actually various ways of constructing one final image. The most basic way to construct an image and show it on a display is to work out the full picture every time, maximizing the work the processor has to perform. In an advanced design approach, it is more typical to have several layers in an HMI, so that if a button has to change color, the CPU only has to rework one layer and not the whole picture. Let's assume our HMI design requires some background, a couple of buttons, and one or two graphs. This would mean we have a VGA-sized background layer of 600 kilobytes, an additional button layer requiring only 150 kilobytes, and an additional graphs layer also taking 150 kilobytes. This would lead to a total memory consumption of 900 kilobytes for the total composition. And again, this is obviously bigger with higher resolution or higher color depth. Next to layering, in order to improve the quality of the HMI, you need to implement double buffering. In computer graphics, double buffering is a technique for drawing graphics that show no or less flicker, tearing, or other artifacts. With double buffering, all drawing operations store their results in some region of system RAM. Any such region is often called a back buffer. When all drawing operations are considered complete, the whole region is copied into the front buffer. Assuming a single buffer size of 900 kilobytes, double buffering obviously doubles the required memory to 1800 kilobytes. The good news for you as a customer of Renesas is that no matter if you design a low-end, mid-range or high-end user interface, Renesas has the right components for your implementation. This starts with RL78 in the low end, which is perfectly suited for segment LCD implementations in metering and medical device implementations. For medium resolution graphics running on RTOS, RX provides you with a very scalable and flexible solution. And in the high end, our RZ family opens the door to Linux and RTOS-based implementations, making use of OpenVG 1.1 and H.264 encoding. As is true with most things, there's a standard way of doing things and a non-standard way. The standard way is usually the way that pops into your head first, because it's based on the trodden path. However, going non-standard can give you the extra edge, and all that is required is sitting down for a minute and evaluate the new approach. Today we want to introduce you to a new approach in HMI design that provides you an extra edge in time to market, ease of implementation, and total system cost. A good part of HMI designers want to speed up their total project time by using ready frameworks running on Linux and differentiate by focusing on their application. By so doing, they automatically are faced with performance limitations inherent to their current platform. On top, the goal is to maximize reuse from past projects and implement fast prototyping. With these ground rules set, the path to the new design seems clear. Choose a Linux implementation, running Qt, and make reuse of past projects, stuff that's sitting in existing folders and cabinets. The advantages of such a project relying only on the past are clear, and every designer values the concept of reuse. The disadvantage, however, is that free software often still means high integration cost later on, and your BOM may be overkill for what you're trying to implement. Let's have a look at what a standard strategy will cost you on the hardware side. The fact that you've chosen a standard microprocessor means that you have DDR memory, which will cost about €3 depending on what your volume is, but it also needs 1.8 volt power supply, and it needs several external resistors and chicken food to support it. So then we have the situation where the microprocessor is very likely in a BGA package. The DDR is in a BGA package, and this means that we need a multi-layer PCB. And the multi-layer PCB can actually cost quite a lot, depending on how big your board is. Let's run the numbers. Having DDR RAM plus passives consumes roughly €3.70. Implementing the three required voltage levels of 1.8 volt, 1.2 volt, and 3.3 volt consumes roughly 45 cents, 50 cents, and 20 cents respectively. In addition, the standard NOR flash will consume something like 50 cents. All in all, the cost incurred for this implementation amounts to €5 35 plus the cost of the microprocessor plus the cost of the multilayer PCB. The final problem with a standard solution is that you can't control the costs of the system. As we saw before, these standard decisions have led us down a path where we now have to purchase DDR memory. This is a graph of the DDR price taken from DRAM exchange over the course of 2013 and 2014. As you can see, there is about a 45% price fluctuation over 1 year. The sum total is that your costs are high and uncontrollable on a product which has cost you a lot of extra engineering effort for integration and due to complexity of design. RZA has many winning features and above all the game-changing 10 megabytes of integrated SRAM that function perfectly as frame buffers in video and HMI applications. The ARM Cortex-A9 core can get code from the external quad-spire memory at very high speeds, which enable execute in place. This means a 3-chip solution becomes a 2-chip solution, minimizing your BOM. The RZA can actually drive 2 LCDs at the same time at WXGA resolution, no external LCD controller required. The outstanding performance is provided by 1000 DMIPS of the ARM Cortex-A9 and the advanced 5X internal memory bus for concurrent transfers of code and buffer information without performance bottlenecks. RZA also has advanced features like single and double precision floating point compliant with IEEE 754, a 2D graphics engine compliant with OpenVG 1.1, and 10100 Ethernet MAC, among others. RZA microprocessors come with 3 megabytes, 5 megabytes, and 10 megabytes of integrated SRAM. For the smallest part with 3 megabytes, you have a selection of 176-pin QFP or BGA package, or a 208-pin QFP package. Please be aware that in all cases the pitch is 0.5 millimeters. RZA1H and RZA1M are fully code and drop-in compatible and come in a 256-pin BGA or QFP or a 324-pin BGA package. Looking at the vastly simplified solution that is possible with RZA, it becomes clear that BOM cost drops sharply with RZA. We don't need DDR RAM and we don't need support components for it. We do not need 1.8 volt power supply to power DDR RAM either. And a pricey NOR flash component can be exchanged with a comparatively cheap quad-spire flash component. All in all, we save roughly €4 35 on this board, and this is not even counting the saving resulting from the fact that we can now use a dual-layer PCB instead of a multi-layer PCB. Next to massively reduced BOM cost, RZA facilitates a much simpler design. Don't forget that in the standard implementation, signals to DDR and NOR flash are sensitive high-frequency signals subject to EMC disturbances. In the RZA case, we only have a few lines to the quad-spire flash components. Let's remember what we have learned in the HMI intro in the beginning of the presentation. What are the operations we have to execute to come to the final image that will be displayed? We have to combine multiple layers that contain background, button, and graphics information. Second, we have to implement double buffering to avoid flickering and tearing using a back and front buffer. And we generally require enough RAM for the raster information to be stored. All this is implemented in hardware on RZA. What is alpha blending? Alpha blending allows for a combination of images through an alpha channel. Each pixel has an alpha level of transparency. The alpha channel defines the transparency of an image. This is supported in hardware on the RZA. What is chroma keying? With chroma keying, a specific color can be defined as transparent in an image, just like the so-called green screen or blue screen in the movies. This is supported in hardware on the RZA. The next question to look at is whether or not we have enough RAM. Here you can see a small calculation about how much RAM you'll need, which mostly varies depending on your screen size. So you'll see that a simple HMI application can be created easily using between 3 and 7 megabytes of memory, leaving more than enough space for the rest of the application. In a standard HMI application, there are lots of things happening on the RAM at the same time. First, the picture data is being read from RAM and sent to the screen. Second, the CPU is running its code from RAM. These two things are happening at the same time. Additionally, RAM is being written to by the CPU in order to create that next picture. This means that there are 3 accesses to this external RAM over one bus happening all at the same time. Wouldn't it be just better and faster if this RAM was internal? With the RZA it is, and the RAM is in fact split into 5 separate blocks, and there are 5 separate buses for those blocks, which means the CPU can read code from one block at the same time as writing the next picture into the RAM, and the current picture can be read out and sent to the screen. All of this happens at the same time and without any blocking of RAM or bus. This means the RZA provides much more performance than other MPUs even running at much higher frequencies. We are now coming to the final section of this presentation, which is an update on tools and software. Very importantly for HMI customers, we have just released the Display Kit. So this solution kit enables engineers to quickly evaluate and demonstrate the leading HMI tools in the industry, accelerating their prototyping and decision-making process. The new displayed RZ HMI solution kit is based on Renesas RZA1 family of embedded microprocessor devices. The solution kit also includes the RZ development board, a WVGA screen, compiler, debugger, and IDE, everything engineers need to start their HMI development once they have selected the HMI software they require. The solution kit also includes third-party evaluation HMI demos from IS2T, which is a Java virtual machine-based implementation, Test Giuliani, which is a very nice user interface, Sega MWin, Express Logic, and then also Renesas sample code. Renesas' new Stream It kit enables designers of advanced security and multimedia applications to develop scalable systems with the shortest time to market, reduced component count, and optimized PCB footprint. The Stream It kit comes preloaded with the H.264 encode and stream demonstration, but can also run 2 additional streaming demonstrations included in the kit. For developers of industrial sensor and home automation systems, the Stream It kit can be used to log sensor status information while sharing the collected data on a web server. For streaming applications targeting the consumer segment, Internet radio MP3 files can be streamed to the Stream It kit, decoded, and played over headphones. This kit also lets you connect a display and allows development based on RZA1L device with 3 megabytes of integrated SRAM. Graphics packages. There are currently many graphics packages available to be used on RZA microprocessors. These are provided by Express Logic, Zagger, Crank, Sirius, ISCT, and Altia, among others. I'm coming to the end of the presentation and would like to highlight 2 very interesting GUI implementations. The first example is an embedded wizard implementation of Tada's GUI running on a RZA board by Emptreon. The solution runs Linux as well as a lean GUI framework inside 10 megabytes of integrated SRAM. You can check this one out on YouTube by searching for Emptreon and Tada. And the second solution is a Crank GUI application running on an XIP Linux by Timesys with very good responsiveness. Very nice demo. Please have a look. So I hope all this information highlighted the flexibility and scalability of RZA-based HMI applications that allow cost-optimized RTOS-based microcontroller-type GUI implementations, as well as Linux-based implementations with or without QSPI memory. So with that, we are coming to the end of the presentation. Thanks a lot for your time, and always think RZ. Thank you very much. Bye-bye.